Well, joining us today on Superheroes of Science, we're pleased to welcome Alexandria Johnson. Alexandria is an assistant professor of practice and research in the Department of Earth, Atmospheric, and Planetary Sciences at Purdue University. So welcome.
Thank you for having me.
We appreciate you taking your time. I kind of want to start with you're a type of gal with her head in the clouds, but I guess it's you don't get your heads in them because you're studying clouds more on other planets, and so it's kind of hard to get your head in them.
Yeah, so we just get to look at them, really. We don't get to fly through them. I do have a background in Earth clouds, so I have had my head in the clouds, if you will. And that kind of led into the progression of learning about clouds in other atmospheres.
Oh, is that how you started your passion then? Is that how you started your passion and interest in what you do?
So my interest started way back in undergrad. I was actually a physics undergrad. And I was very much like, I'm going to do something super theoretical and like cutting edge and, I don't know, topological insulators, something very, showy. And it came to doing a senior research project. And I was like, well, actually, I don't want to do something theoretical. I want something I can watch. And so I found a researcher in my department who, Dr. Will Cantrell at Michigan Tech, give him a little shout out, who studied ice nucleation. And I went to school in the Upper Peninsula of Michigan where we get like 300 inches of snow a year. So like you're surrounded by it. And I was like, this is great. I can learn how this forms. And this is going to sound really lame, but I watched water droplets freeze and I thought it was the coolest thing. And he was like, oh, well, you can go to grad school and you can study clouds in Earth's atmosphere, like fly planes through them and look at the actual particles. And I was sold. I was like, this is what I want to do with my life. And so I actually came here for my graduate degree as well in atmospheric science. And sort of over that time frame, I just really got interested in, how we can take microphysics, this tool to figure out the small scale processes of like how cloud particles form, and we can take it and apply it to different systems because it's really universal. It's physics. Like that's what I love about it. And so I started thinking more about, what would clouds on other planets look like. So like Mars is a really easy one because it also has water ice clouds, but it also has CO2 ice clouds. So you get lots of crazy things happening. And then I got this opportunity to work with Dan Sitzo, who's our department head, and Sarah Seeger at MIT for my postdoc, because they were looking for someone who could bridge that gap between Earth science and other planetary bodies and really focus on clouds. So I kind of fell into this opportunity and I'm very grateful for it.
Oh, awesome. Well, man, let's start with a short overview of the foundations of, as you talk about like the physics of cloud formation and stuff. And so can we start with that and have you kind of explain how clouds form? Because I know I got a bunch of questions about the clouds made from things other than water. That I'm like, oh, how's that going to happen? So I guess we need to maybe back up a hair and make sure everyone's on the same level understanding how clouds here form.
Definitely. So we think about the air around us is mostly nitrogen and then oxygen, and there's some water vapor in it when we think about Earth. And we have a lot of different processes by which that air can be lifted into the atmosphere. And when it lifts, it expands because it's experiencing a lower pressure. So its temperature reduces. It also experiences a lower temperature just by going up in the atmosphere. So, if you go up on a mountain, we don't have them around here, but if you go up on a mountain on a sunny day, you'll notice that the temperature gets colder as you go up. And so the air that we're lifting from the surface experiences that too. And you get to the point where that water vapor no longer wants to be a vapor, it wants to be in the liquid phase. And so it'll condense out onto basically dust particles in the atmosphere, and you get the formation of clouds. You can then go on and keep lifting it higher and higher, and you'll get to the point where either that water doesn't want to be liquid anymore, it wants to be a solid, so ice, or the vapor wants to move into the ice phase, and you can start thinking about multiple different phases of a substance and what's happening in the cloud with regards to those particles.
Now, you said Mars, and that kind of caught me off just a little bit, I got to admit. It doesn't happen too often, because I know there's no liquid water on Mars. And I didn't think there was even like ice exposed at the surface because it would sublimate out. But
so there is some at the caps, the polar caps in the winter. We get a lot of CO2 being pulled out. There's also, liquid, ice CO2 ice, and then water ice being pulled out as well from the atmosphere. But the atmosphere is mostly CO2 and there's not much water around. So yeah, you kind of have to dig under the surface to get to water ice, and then it'll sublimate right away into the gas phase.
Okay. And so how does the cloud thing work there then?
Yeah, so Mars is pretty interesting in that even though its atmosphere is dominated by CO2, which we think of as a greenhouse gas, it's really, really thin. So our surface pressure is about 1,000 millibars. On Mars, it's 6 millibars, so it's much, much less. And what we end up seeing is that there's about 100 degree Celsius or 100 Kelvin swing in the day to night temperature. And during that temperature swing, you can reduce the temperature of the atmosphere enough that you're going to get water ice condensating out, or it actually deposites. It goes from the gas to the solid phase. And then that's sort of at one layer, a little bit lower in the atmosphere. And above that, you'll get CO2 ice clouds forming.
So does CO2, does that form the same way a water cloud would?
Yeah, so the basic physics is the same, is that you have this gas around in the atmosphere and you're cooling it to the point that that gas is no longer, stable in that phase. So it wants to move to something new. And in the temperatures and pressures that we look at for the Martian atmosphere, it wants to go from that gas to a solid.
Okay. Well, that makes sense. Okay, that's a little better for me. But okay, and I see how we can see those on Mars, because I mean, we have satellites going around Mars collecting data and stuff.
We have so
your
much
research is a little further out than that.
Yes. So we do think about Mars still, but we've really turned our eye towards exoplanets because there's so many questions about what's going on these planets. We have transits and occultations. So a transit was when the planet passes between the star and us, and we can observe a dip in that star's brightness. And when that happens, sometimes you can get a little bit of starlight that's filtered through the atmosphere. And we know from looking at atmospheres around us in our solar system that that light can be absorbed by molecules, and you can basically get imprints of the molecular composition of that atmosphere on that starlight. So we can start to think about what are these atmospheres made of. We can then do basic what we call radiative balance calculations. So how much solar or stellar radiation is going into the planet versus how much radiation is coming out. So how warm is it? What sort of compositions are holding on to heat? What can that do for how the temperature and pressure change with height? And then we can think about what sort of clouds might form in these atmospheres.
Wow.
Okay, so for me, how is an exoplanet different from Earth? Like is there a difference?
So exoplanets, that term in the Latin sense, exo means outside. So it's a planet outside of our solar system. So a planet around another star. When we look at the demographics for exoplanets that we've found, so what properties do they have? What might they represent in, if thinking in terms of our solar system, which is kind of our blueprints, we tend to find planets that are called either super Earths. So they're bigger terrestrial planets, bigger than Earth, or sub-Neptunes. And so they're gaseous planets that are a little bit smaller than Neptune. But we don't have this type of planet in our solar system. We also find things like hot Jupiters, which are Jupiter-sized planets, or larger, much, much, much closer to their star. They could have orbital periods. So like 1 year on that planet could be a couple hours or a couple days in Earth time.
Oh, wow, that's moving.
Mm-hmm.
But how do you know? It still trips me. I'm trying to grasp, because it's out there more than one way in me, but I'm thinking, okay, you're looking at this planet, and so what kind of wavelengths are you using to look at to determine the composition of the clouds on a planet that's pretty darn far?
Yeah, so I should preface this. I'm not an astronomer, so I don't do the observations. I just use the data from the wonderful astronomers who do them. So there's a wide range of wavelengths that we can look at these planets with. The warmer planets are going to emit in the infrared, or IR. So when you think of anything around you is emitting radiation, just because we all are absorbing some radiation, so we're re-emitting it. and a body that is at normal sort of temperatures, so like you or me, or we could go and look at the moon or any other planet in our solar system, we can basically get an idea of the temperature it's at from its IR. And so in ways we can sort of tune the wavelength that we're looking at it in, and we can sort of probe different depths in the atmosphere or different substances in the atmosphere. And so IR is a really useful technique. Spitzer Space Telescope used to be around. It's no longer operational, but that was one instrument that was used a lot. Another instrument that has sort of a wider range of wavelengths is Hubble is now used to study exoplanets. The Wide Field Camera 3 is one that has been used to characterize those transits that I was talking about, to look for signals for atmospheres. And you just kind of basically use as much of the wavelength spectrum as you can from the instrumentation and pull out all the information you can. So another way we can look at it is in the visible spectrum. And so instead of thinking about something that might be, I don't know, 200 Kelvin radiating back at you in IR, you can think of what we see, and we can get light that's scattered off of planetary atmospheres back to us that can give us an idea of what might be in that atmosphere, like clouds or hazes.
Oh. So you understand how the physics of cloud formation, and is it at that point, do we make the assumption, and if so, how safe of an assumption is it, that the physics of cloud formation on Earth would be consistent with the physics of cloud formation on a body orbiting a star with a different mass 5 million light years away?
So that physics is universal, and that's what's really so great about it. If you talk to any of my students, I think in every class I've taught and all the students that I advise, I have this saying that we have this little template, and we go and we look at Earth and we say, okay, this is our physics that we can study really, really well. Like I said, we can do this in the laboratory. We can take planes out and look at things in real time. We have really in-depth models. We've been observing Earth for an extremely long time, so we have lots of data. And we can take that physics template and turn around to another planet and say, okay, how does this template fit what we see on Earth? And then the basic physics is the same, but you have to sub in, different planetary conditions. So what is the composition of the atmosphere? What is the temperature? What is the pressure? How much radiation do you have coming in? And start to add in those details for that specific planet. What's nice about this, and this is how I view it from my background, is that, we take this template for Earth, we apply it somewhere else, we learn something about that planet, but we can also turn around and we can learn something about Earth. So maybe we can learn about the early Earth or things that might have changed over time. We don't expect that our atmosphere was always like this. We know it wasn't. We had great oxidation event. We humans are changing our atmosphere. And so we can kind of make it a nice little feedback cycle of learning about other planets, but learning about our own in that way.
I love how you're talking about using all this data that we have and then looking at data from other exoplanets and fitting it into that template that you said that we know and we can study here and then compare that to other places. How much of a process is it for you to take that? You said you use the data that's collected by astronomers. Mm-hmm. How much work goes into getting that data to a point where you can start making those comparisons?
So what usually sort of happens with the data is astronomers will go out and they'll collect this information on a planet, whether it's that little bit of light that's been filtered through the atmosphere and you get a constituent. So say in hot Jupiters, we see there's sodium and potassium lines that are usually very clear. And so we know that those substances are there. Other people will then take these and feed them through models to try and think about what the atmospheric composition is, what is the temperature pressure profile. Our work can feed back into that, but right now what we're doing is we're taking that information and sort of pulling out what are the types of clouds that might actually be in these atmospheres. And then we're saying, okay, well, let's help out these astronomers and these modelers by trying to reproduce those particles in the lab and look at how they interact with light, whether that's by scattering it or adding some more information onto that light through polarization.
Oh, and so Well, oh man, too many questions all at once.
Okay.
And it all came to me. And so what are some of the most common clouds made from other planets?
Yeah, so in the lab, we've really been focusing on that sub-Neptune planet range. So once again, that's a gaseous planet that's smaller than Neptune, but it's bigger than Earth. So we think it has a very hydrogen helium dominated atmosphere like Jupiter, Saturn, Uranus, and Neptune. The reason why we picked that is because the upper atmospheric temperature is about 500 K, which is a temperature we can reach in the laboratory. And that's kind of important. We'll talk about the hot Jupiters in a second. But for those planets, we think that there are potassium chloride clouds. And potassium chloride is something that you've probably experienced but haven't known it because it's a substitute for table salt. And then zinc sulfide clouds, which is a mineral, right? When we go to the hot Jupiters, these planets are thousands of Kelvin, extremely hot. Remember, they're really close to their star and they're zipping around really fast. And so there we think of more metallic materials. So enstatite and forsterite, which are minerals that you could go out and find in your local region. Titanium oxide is forming clouds in these systems. There's going to be iron-bearing minerals. We're talking about things that we would not think of as clouds at all.
That's just crazy. I mean, to think of, I'm looking at a metal cup here and I'm thinking, wait a minute, it's hot enough that's in gaseous form and make clouds?
Yes. One of the really fun things when we're doing like K through 12 outreach for this is that it's theorized that some hot Jupiters rain rubies because it's corundum. And so you can think of like it wouldn't be as pretty, right? It's not polished rubies falling from the sky, but you could think of a ruby rain.
Huh. It sounds cool until you realize the environment it is. It says we couldn't survive in it.
Yeah, exactly.
That kind of reminds me, I think I've heard before, but since we're talking about Neptunes as well, I've heard before that it could rain diamonds on Neptune. Is this a possibility?
I know there's helium rain.
Okay.
Thought to be in the gas giants, but I haven't heard about diamond rain. And maybe that's just because it would be more towards like the high pressure, high temperature regimes, deeper in the planets that I don't really think about. I think about everything that we can see at the top and the cloud levels.
Okay. I remember reading something. I thought it was about methane and things, but I thought, no way. But I've never heard of rain rubies. That's really cool.
All right. So tell me about your lab. I want to know about that then. You're modeling things to help support our understanding of things millions of light years away. How in the world are you doing that?
Yeah, so we have a couple different techniques that we use. All of them require us to come up with an aerosol or what we would call a cloud particle on these planets. So that zinc sulfide, that titanium oxide, we procure them from just the regular suppliers for chemistry stuff, or we can get them because these are minerals on our planet. We can actually get them from the geology part of the department, which is pretty fun. But we either do systems where we look at an ensemble of particles, which is many particles flowing through a laser beam and looking at how they scatter light, or we can levitate a single particle, expose it to some very specific conditions. So up to 500 K is the temperature for that system, and shine a laser light on that and look at how it scatters and polarizes light. And both of these have their utilities. The ensemble system is very much like Earth or any planetary atmosphere. If we were in the same room, I'd say, there are hundreds and thousands of aerosols between us. We can't see them, but they're always around us and they influence our climate. And the same thing is true, on any planet. So, having that mixture of particles is really important for what we expect out of a real atmosphere. But the system where we levitate a single particle gives us a lot of control. We can have that single particle that has a charge on it, and it's held by voltages and electric fields. And we can keep it there and we can watch how it changes with time. We can maybe nucleate another substance onto it. So say use it as a CCN, because in these or cloud condensation nuclei, I'm trying to get away from the jargon. It's hard sometimes.
I was going to ask.
But we think in these exoplanet atmospheres, particularly the gaseous planets, that there's not just one cloud or two like there's on Mars. There's many, many different layers of clouds, and these layers of clouds are going to feed into each other. And so a cloud that could form lower that cloud particle could then act as a condensation nuclei to help the next cloud layer form, and so on and so forth. So we haven't gotten to that nucleation part yet, but that's really one of our big goals. We're just kind of using the minerals that we have now to really learn about what we see from these particles that can influence radiative balance on the planets, can influence what we're seeing, or the astronomers are seeing in their observations as well.
So how big is, I mean, I'm trying to envision what this looks like in your lab. Definitely trying to envision it. And so I mean, okay, you have this big chamber, and it's how big? What's my scale?
Yeah, so let's see if I have anything around me that can help with this. So our single particle system is about 6 inches wide. It's basically a cylinder that we have our experimental volume in. So it's about 6 inches wide, and I think it's a couple centimeters tall. And then this area is enclosed by a quartz ring. I believe it's quartz. It's coated, and it's got some to keep reflection down, so we can actually get our signal out. And then on top of that, there's 2 pretty bulky copper plates that we can set to different temperatures. So we can set up a temperature gradient. When we get to nucleation, we can set up a vapor gradient in there, and it's very well controlled. So that adds like 2 inches on the outside of it, but it's fairly small. We do have a big box that goes over it. So when we do get up to 500K, we're not melting anything we're not supposed to in the lab. But the system itself is quite compact.
How do you get it that hot?
We use recirculating baths. So you have this system that has usually a siliconated oil in it, and it will heat that oil up, and then it flows it to the 2 reservoirs at the top and the bottom that we have to reach those temperatures. And our system is also unique in that we can set the top to a different temperature than the bottom, so we can get those temperature gradients across it, which is beneficial for when we do nucleation studies.
And so you have some kind of sensors inside that small of a thing that you're measuring wavelengths and.
So the laser light is external to that. So we use a single, unlike sort of the observations that go on, we use a single wavelength laser, and that's so we can have really precise control over what we're detecting. But these lasers are basically, they're cute, they're tiny, they're like this big, and you can plug and play them, so you can change out your wavelength pretty quick, and you can continue your experiment. Outside of that sort of, I should have brought a picture up for this, but we have our particle that's levitated in the system. We have our laser beam coming in, and then on that same sort of level where the laser beam is, we take what's called a photomultiplier, and we sort of spin it around our system, and it collects the photons that are scattered by our sample. And so that's how we actually get our physical data on what these particles are doing to the laser beam.
Wow, it's collecting individual photons?
We can, well, with this photomultiplier, we can count the photons, or we can just get out a voltage or a current, which is equivalent to that. So we could, if we wanted to, count the photons, but our laser beam is really strong, so we would have very high numbers.
Okay. Well, that's just amazing. Totally trips me up that you can do that. I mean, I'm just saying, you're modeling something to see, how we measure things that's light years and then some away. I mean, it's how far away are we looking at some of these exoplanets?
So the one that we use as our sort of base model is called GJ1214b, because they all have a catalog number. I should say, so that GJ1214 is the star number, and then B means that it's the first planet that was detected around this star. I think it only has 1 still, but if you ever see like B, C, D, that means there'd be 3 planets around that star. That planet is about 42 light years away. So it's, not a short distance, it's very far away. One of the things that I think is so cool about the exoplanet information is that the information that we have on these planet and star systems, it's only a couple pixels on a telescope that like you're actually getting the data on. And you can't resolve the planet from the star. So it's really this, the classical way to describe it is that it's a firefly next to a spotlight problem. And so you have to pull out the information that you know about the star to learn about the planet. And you get the, part per million signal, but we can still pull out all this atmospheric constituent. We can still think about the temperature, like day-night temperature differences on these planets, and get a ton of information from such a, what you would think would be a small, insignificant amount of data on those couple pixels.
I'm so glad you said that, because I'm thinking as you're talking about this cannot be very much. I mean, that's so small, because I just think how far it's away. The data you're getting would have to be tiny. So that's an excellent explanation then, that, it's a couple of pixels, and that you're, like you said, using what you know to take that out so that you have that data. Wow.
Yeah.
It's just inconceivable you can get that much data from that small of a thing. And you can, using basic assumptions and be able to determine all kinds of things about it.
Yeah, I love it. There's sometimes I'm reading the papers and I have to take a step away, because my mind is just like, wow, how are we doing this? I have to go outside and look at the real clouds, on a sunny day, and then I have to come back to the paper. It's absolutely amazing, and we are just learning so much about planetary systems, and what is the diversity of planets that we can have, and what does that mean for an atmosphere, or if there's a surface there, what does that mean for the surface?
And so what all, with this type of research, what all are we hoping to gain from it? And you've already kind of mentioned a couple things. I just want to, hit them on the head harder or whatever. But you've already mentioned a couple. So what all are we trying to gain through your research?
So what we want to really do is we want to make the gap between what we observe and what we model more realistic to what is actually happening. So we observe an exoplanet. In some cases, we don't get that signal transferred through the atmosphere because there are clouds there and they're optically thick. And so you kind of left with this question of, well, we know that this planet isn't massive and dense enough to just be a bare rock hurtling through space. It has to have an atmosphere. It's rather puffy, or you can think of it as being light in terms light density. And so if we want to know what's happening there, we need to know something about the clouds, the particulates that are present. And so we can use other information. So I mentioned there was the transit when the planet passes in front of the star. There's the occultation when it goes behind the star. And then if you can look at the entire orbit of that planet, it's called the planetary phase function. And through that phase function, you can look at light scattered off of the planet and back to us, the observers, by angle, which is basically what we can do in the lab, just a little more simplistic, having our single particle and taking a photomultiplier around it. But it's the same thing. And so we can kind of take that data that an astronomer has found, whether it's information on the atmosphere or information on that scattering on that particle, or excuse me, that planetary phase function, and we can do it in the lab, and then we can give that information back to the modelers and say, well, here's a better representation of what those clouds would actually look like in the atmosphere. And that can help us better understand temperature pressure profiles, which helps us better understand the chemistry, the cloud formation, what might be below that we can't see. Is there a surface, or what sort of compositional changes are there? Really, it's funny because astronomers see clouds as a nuisance because they can block their view of these planets, whereas I see it as a benefit. Like, we can use this to our advantage to learn what we can't otherwise see.
So do you ever come across something and then you're working on the data and looking at it and you're like, no, this does not make sense. What do you do if you hit that point?
Well, there's some interesting things in that. There have been some modeling work that has been done where we basically just do equilibrium chemistry, and it's a very simple guess. So you have a temperature pressure profile, and you lift that air along that atmosphere along that profile until you get to the point where the gas wants to be in a new phase, and it either condenses or deposites out. So going from the gas to the liquid, or the gas to the solid phase. And we know from our own experience on Earth and other planets that it doesn't happen right away when you reach saturation. So, you can reach 100% relative humidity, but you might not get a cloud. And so that's something we think about a lot, is what is that then going to do to where these particles form or what they're made out of? What is that going to do to the temperature pressure profile in the atmosphere overall? It's not necessarily like it's completely wrong, but we have to start thinking about the intricacies of this because we're getting more data, and that's kind of the end goal, is to really be able to explain these planets as well as we can our solar system neighbors.
Very nice. Well, thank you. This was really cool. This is really cool. It just blows my mind to think that you can take that a couple pixels, and you can actually determine information.
Right.
It just absolutely blows my mind that you can start having an understanding of planets that are that far away simply through a couple of pixels. And I can only imagine how much you'll learn when technology it's always growing. It's always better and better. I know it's like, your cell phone camera is just blows away what it was 10 years ago. Yeah. So I can only imagine the level of the telescopes and stuff that you use, that as those increase in technology, I'm guessing there'll be a whole line of people to get that data for the whatever next telescope we push.
Oh yeah. The next one, the one that the exoplanet community's basically been waiting on for a while is the James Webb Space Telescope, or JWST. Its launch has been sort of pushed back with time because of things that were detected here that needed to be fixed before it got launched. Its date for launch is actually October of this year. So very hopeful that it actually goes up there. We really think it's going to be a whole new window into exoplanet properties and their atmospheres. So I'm excited for it. It's going to be looking at a whole bunch of different wavelengths, and I'm really hoping that it gives us more information so we have more clouds that we can study.
Awesome. Well, thank you for your time. We
No worries.
really appreciate it.